Welcome back to Water Resources. In this third lecture for the Fluvial Geomorphology module, we're going to talk about the processes that shape channels. That's the question we've been leading up to so far, and here we're going to get into the nuts and bolts of that, specifically the types of flows that do the work. And before we really can go too far with this, we need to get some nomenclature down, and pay attention here because these terms can be a little bit confusing, although I've tried really hard to sort them out for you and make them a little more accessible. So first of all, effective discharge. An effective discharge is a discharge that's able to shape the channel. In other words, it can do work. Now here's the thing. There's more than one possible effective discharge. Any level of discharge that can move sediment around in a way that's significant enough to change the shape of the channel, move some sediment, erode a bar, deposit a bar, erode a bank, deposit somewhere else, is effective. So we know that base flow generally is not effective. Generally at base flow the stream's not doing any work. You can stand next to most streams of base flow and see that the sediment's really not moving. And even if you have a flow that's a little bit greater than base flow, might be a little bit of suspended sediment moving, but probably not much going on in the channel in terms of moving the bed or eroding the banks. So an effective discharge is some flood that's larger than base flow, but it doesn't have to be all that big a flood. Alright, then we've got the next term, the dominant discharge. Dominant discharge is the effective discharge that does the most channel shaping work over time. Okay, so the dominant discharge is an effective discharge, but it's a specific effective discharge. It's the one that works the most efficiently. So a really big flood, like a monster flood, that can do a lot of work. But monster floods usually don't occur very often. So they might do a lot of work and then not occur for 10, 100, 50 years, some long period of time like that. So averaged over time, they may not contribute that much to the overall work that's shaping the channel. On the other hand, a flood that happens a lot but does just a little bit of work may not be all that significant either. So we're looking for the balance between a flood that happens frequent enough to do a lot of work even if it's not that much. So that it's a combination of frequency, how often it occurs, and magnitude, how big it is. In most streams at equilibrium, remember in the last lecture we talked about what equilibrium means. In most streams at equilibrium, the dominant discharge will be morphologically equivalent to the Bankfull discharge. The Bankfull discharge is just what it sounds like. It's the discharge that just fills the channel up to the top of the banks. All right. Now, there's a caveat there. It says at equilibrium. If a stream is not in equilibrium, then the dominant discharge may not be the Bankfull discharge. Those two things can get out of sync. Okay, so let's talk a little more about Bankfull discharge. As we mentioned, assuming the stream is in equilibrium, Bankfull discharge will normally be the dominant discharge. Now this is really important. You might think about, why is it that this Bankfull discharge is so important? Why is that the dominant one? Well, because of that efficiency we were talking about. When we have the balance between a flood that happens frequently but is still of a high enough magnitude to do a significant amount of work, so we're balancing how frequently it happens with the amount of work it can do. So when we hit that balance, we're going to find the stream is going to adjust to that balance, because when we're at the optimal balance between those, we're going to have a good efficiency in being able to transmit flow. In the Bankfull discharge, Bankfull is describing a morphology. This is the discharge that is just the level at which the water has filled up the channel to the point that if any more water enters the stream, it's going to spill out onto the floodplain. Now think about it. The channel might be 6 or 8 feet wide in a small stream, or maybe in the Mississippi River several hundred feet wide, but in that small 6 or 8 foot wide stream, the floodplain might be 500 yards wide. So it doesn't take much more water when you're in the channel between those banks that are maybe 6 feet apart to raise the water level 1 more inch. That doesn't take a whole lot more water. But once you spill over into the floodplain, now instead of raising width 6 feet across 1 inch, you've got to raise a width 500 yards across 1 inch. That takes a lot more water. So at that point, the water gets spread out across all the floodplain. The floodplain's got a lot of friction on it, all the vegetation, people's houses, structures, trees, all that stuff is increased friction. So it's just not that effective once the flood gets that big. And you've got to add a lot of water into the system to get just a little more bang for your buck. So the best bang for the buck is when that water is right up to the edge of the banks. That's as steep as we can get the water and still have sort of an efficient frequency of flow that can happen enough to be efficient at changing the channel. Okay, so let's look at the definition of bankfull stage. The bankfull stage corresponds to the discharge at which channel maintenance is most effective. That is, it's generally doing work that results in the average morphological characteristics of the channel. So it's not that the stream is adjusting to the size of the channel. It's that the stream is adjusting the size of the channel to this common flow that happens with a certain frequency and magnitude that makes it the most efficient for transporting sediment in the system. The bankfull discharge fills a stable alluvial channel up to the elevation of the active floodplain. This discharge has morphological significance because it represents the break point between the processes of channel formation and floodplain formation. A little bit different way to look at it. Alright, so here's an example. This is the confluence. Coming in from the left side here, we have Canfield Creek, and coming in from the right side, the south branch of the Root River in southeastern Minnesota. So this is a confluence of two streams. This is at base flow conditions. If you look at this sort of clump of trees here right at the point of the confluence, that's this clump here. Now obviously the picture at base flow on the right here is in leaf off conditions in the early springs, maybe just a few leaves on. Here's like full summer. This was in August or June, I think. And so we have the full vegetation out, but that's the same tree right here as right here. And so this is bankfull, or very near to bankfull. You can see the water over here is just about up to the edge of the floodplain, so it's several feet deeper than the stage we see here on the right. Here's a cross-sectional survey. You can see we had a total station here. We were surveying this stream. We got this base flow survey. We've got the channel cross-section morphology. At base flow here, the picture on the right, the stream's at about this blue line level. That's base flow. On the left, the picture is approximately at the left line. You can see it's just about filling up the stream channel. To get any deeper, it's going to have to flood the whole floodplain, and we're not showing the whole width of the floodplain in this cross section, just the parts within, looks like 15 or 20 feet of the channel, but this floodplain is several hundred yards wide at this point. So getting any deeper than this, we're going to have to fill that whole floodplain that's several hundred feet wide. On the Canfield Creek side, you can see it was also a bankfull event for Canfield Creek. Another example, this is Pleasant Valley Creek. We looked at Pleasant Valley Creek stream gauge data for the August 2007 flood in a previous module. This is that bankfull flood. This is the morning after the August 2007 flood. You can see that the peak flows were actually over bank, so they were greater than bankfull. Deposited stuff up here on the footbridge. You can see the weeds knocked down up here in the bank. It spread out across the floodplain. And this is the morning after when the flood has receded back down to just about a bankfull level. So you can see that that's probably 5 or 6 feet above base flow level at the stage it's shown in the picture. And when it was out over the floodplain, it was another couple feet deeper than that. All right, so let's talk about this effective discharge. Effective discharge, as we talked about earlier, is any discharge that can do channel shaping work. Okay, any discharge that can shape the channel. The graph here shows a frequency curve. So the peak of the frequency curve would be the most common frequency event. That would be the base flow event. Most days of the year, depends on the stream, but let's just say 340 days of the year, most streams, I'm picking that number out of the air, but most streams may flow at base flow 340 days a year. Okay, so that's going to be the most common, most frequent event. All right. As we get lower flow events, maybe during really dry periods. Those are much less frequent, and then the frequency drops off as we get bigger and bigger discharges, and our biggest discharges are really infrequent. So let's just say, hypothetically, this is a 500-year flood out here. They only happen on average once every 500 years. So they're very big, but they're very low frequency. All right, then we have a sediment discharge rating curve. Well, these high-frequency flows like base flow don't really move any sediment. So you'll see the sediment discharge curve doesn't even start there. It's essentially zero. As we get out here to these lower frequency flows, we see that somewhere in this range we start to get a measurable amount of sediment discharge. So our first effective discharge is right in this range right here. So all the discharges that show up on this curve out to this, to our most rare floods, are effective because they're moving sediment. If you're moving sediment, you're shaping the channel. Now, if we multiply the frequency by the amount of sediment, don't worry about the units here, but it's a product, right? A product is when we multiply one thing by another. So we multiply frequency times sediment discharge, we get a product of the, and that product would be magnitude times frequency. Now, wherever we have the maximum product, so where whatever two numbers, this dashed line here is where this product curve peaks. And under that, this sediment discharge multiplied by this frequency gives us the greatest product. That's the dominant discharge. That's the dominant effective discharge. That's what the dashed line would be. All right, so let's go through this one more time just to make sure you've got it. We've got our flood frequency curve. We're going to color that yellow just to highlight that. Our peak frequency would probably be base flow in most streams. And as we get to more and more larger discharges, we have more and more infrequent flows. Our sediment moved, so our sediment yield curve is the blue one. The least frequent flows, like a 500-year flood, they have the size and the power to move a lot of sediment, but they don't happen very frequently. These very frequent discharges over on this side of the curve, they don't move very much. But somewhere in the middle here, we get a spot where we get an optimization between the two levels, and that's the peak of our product curve, the product of frequency and magnitude. So when we put all this together, okay, flood frequency times sediment moved equals dominant discharge, or the maximum product of flood frequency times sediment moved equals dominant discharge. So in this hypothetical stream, the dominant discharge is where this product curve maximizes or peaks. It's not the biggest discharge in terms of it's not the most frequent, it's not the least frequent, it's sort of an in-between. It's not the discharge that can move the most sediment. It's sort of in between, but because the frequency is high enough and the amount of sediment moved is high enough, when you put them together, you get that dominant discharge that is going to correlate in a stream at equilibrium with Bankfull discharge. So what we're talking about is a Goldilocks thing. Not too hot, not too cold, not too big, not too small, not too frequent, not too infrequent. So the moral of our story then is big floods move lots of sediment, but they don't do it very often. Small floods move small amounts of sediment, but do it quite often. The dominant discharge is the balance between these two things. A big enough flood, but not so big that it doesn't happen very often, and a small enough flood that it can happen a lot, but big enough that it can still move a fair amount of sediment. In most streams, that dominant discharge, that Bankfull discharge, occurs every 1 to 3 years. You'll find different sources that cite different numbers, 1.5, 2.5, 3 years, 2 years, whatever, but it's somewhere in that range of 1 to 3. So these are fairly frequent. In 100 years, there could be 100 of these floods, or there could be 33 of these floods, or somewhere in between. So they're happening every couple of years. And so remember, to sum this up, normally, dominant discharge equals Bankfull discharge if the stream's in equilibrium. If it's out of equilibrium, the dominant discharge may not correlate to that morphological discharge that would be Bankfull. All right, we're going to end it there. That concludes the lectures on our channel shaping. Hopefully this gives you a good idea of how channels are shaped. It's this combination between flood frequency and flood magnitude. We've covered a lot of different aspects of channel morphology in this module and in the hydrology module earlier. So hopefully you have a good handle here about how streams are changed by natural processes. In this module for Fluvial Geomorphology, I've also given you a number of reading assignments and some YouTube videos to watch from some other sources that are going to talk about channel restoration. And when you listen to those, what I want you to pay attention to is that channel restoration is about identifying what constitutes an equilibrium condition, quantifying or at least identifying some goals, like what's the purpose of the stream that you want to restore. Do you want to restore it for ecosystem, for habitats, for recreation, for human usage, for boating, whatever? And you've got to maximize the potential of all these different variables so that the stream can function with the natural flow regime in which it exists. All right, thank you for your attention.